This podcast is on molecular solids with a specific look at carbon. It is a special kind of atomic solid because there are three types of solid carbon. This is a good way to give us an understanding of the three kinds of molecular compounds that we get as solids: amorphous, diamond, and graphite. How are the atoms in these solids put together? Because that's what explains why they're amorphous, or diamond, or graphite. In diamond, every single carbon is sp3 hybridized, and it's connected to four other carbons. So what we actually have is a network covalent solid with very strong sigma bonds in a huge molecule giving its hardness. And in fact, when diamonds are cut, they're actually broken along areas where there are no bonds due to errors in the crystal. Why is diamond an insulator? Well, it's because the electrons are needed to be shared in the covalent bonds, and they can't move around. If you think back to metallic bonding, it conducted because the electrons were mobile. Graphite is different. In graphite, each carbon is connected to three others, and it's sp2 hybridized, and so you have that p orbital, where electrons are therefore above and below the planes. And indeed, this flat molecule is some six-membered rings, and it can move. Those pi bonding are above and below the plane, and because of it, the electrons are free to move throughout. So graphite conducts electricity, and the layers actually can slide by on each other, so it's used as a lubricant in things like locks, where you don't want any greasy things that will pick up dust. It's actually a rather interesting material. Now, there are also molecular solids where molecules occupy the corners of the lattices. Different molecules have different forces between them, and the forces depend upon the size of the molecule and whether or not they're polar. And if there are no dipoles, you usually have only London dispersion forces. And, well, large molecules such as iodine can be solids, waxes, some plastics, but really, more of the solid molecular compounds are those with dipoles, and indeed those also with hydrogen bonding. But no matter how strong the intermolecular force, it's always much, much weaker than the forces in actual chemical bonds. The stronger the force, the higher the melting point, the higher the freezing point. And those are the things that we commonly will be comparing when we're looking at forces of attraction. Just to finish, ionic solids are sort of at the extreme in the dipole-dipole system, because in the actual fact you're held together by opposite charges in large crystal lattices, and so the intermolecular force of attraction is actually an ionic force between ions, so the melting points are incredibly large. The atoms are locked in a lattice, so also they're brittle. When you drop them, they break. Every electron is accounted for, so in fact ionic solids are very, very good insulators. Unless, of course, you melt them or dissolve them, and then you have free ions, and they conduct electricity.